All right, so let's see. We left off on page 152. We pretty much finished this. Hopefully after yesterday's homework, you guys are good with matching boxes to probability histograms. So there's two things that we talked about on Tuesday that were important. The first one is this, the central limit theorem. Central limit theorem says that the probability histogram for all sums, averages, or percents of draws from a box will get closer and closer to the normal curve as the number of draws increases. And this is going to be how we do all of the stuff that we're doing today. So this was super important. And then the other thing is, so, okay, that's great. As n goes up, the histogram gets closer and closer to normal. But how big does n have to be? And we said that depends on our box. If it's a lopsided box like this, it's going to take more draws to look normal. If it is a nice normal box like this, it's going to take less draws. So those were basically the key takeaways from the other day. I also wanted to point out different ways that you can recognize which histogram goes with which box. So here, with these, they tell us these two are for box A, these two are for box B. And another way to think about this is to look at what's in the middle. If you have a histogram with a lot of bars, like all of these are 25 and 50 draws, the middle, so this number right here, 50, right here it's 100, here it's 100, here it is 200. Those numbers are all the expected value of, we're dealing with sums. So these are the expected values of the sum. And you could, if you wanted to, if you were matching these up, you could figure out what that is. Because we know with this box, the expected value of the sum is just n. So for this one, for the first histogram, n is 25, okay? Times, and then the average of this box. And the average of this box is 2, so I end up getting 50. So that's why 50 is right here in the middle. So that's kind of, there's a bunch of ways, if you have to do this on the test, to match up the histograms and boxes. That's one of them. You could think, okay, what's the expected value? That should be right in the middle. All right? Any questions on that? Okay, we'll start with this. So this is the second part of the probability histograms chapter. And here, okay, what are we doing? So this is called the normal approximation, except now this is the normal approximation for random variables. So we're going to go back to basically chapter 5 and do the same thing we did there. And it says right here that we can use the central limit theorem and then use the normal approximation. Basically, we can say that if our n is big enough, we don't have to draw a probability histogram. We can just use the normal curve as the probability histogram. So that's what we're going to do. And then we can answer questions like, it says you can use the normal curve to calculate the chance that the sum of a number of draws falls in a given range. So our first question, let's just look at 7a. It says in 100 coin tosses, what's the chance of getting less than 45 heads? All right, so what we want to do basically is say, okay, we have 100 draws, right? We're tossing a coin 100 times. N is 100. And with 100 draws, it says since there are 100 draws, we know that the histogram will be very close to the normal curve. So we can just use that. I don't have to draw a histogram. That'll take forever if there's 100 draws. But I'm just going to use the normal curve. And basically, I'll mark 45 heads on this curve and shade the area to the left to figure out the chance of getting less than 45 heads. All right, so we need to, it says, so there's 3 steps. Step 1 is to draw the box model. Step 2 is to find the expected value in standard error. And then step 3 is to use the normal curve. So that's what we're going to do. So for a fair coin, this one is super easy, right? A fair coin, we know there's 2 tickets in the box because you can either get heads or tails. And we're counting the number of heads, right? Getting less than, we're interested in the heads. So you can either get 1 head or 0 heads. And we would essentially say, if I'm flipping a coin 100 times, that's the same thing as drawing. That's the same thing as if I draw 100 times with replacement and take the sum. All right, so we're simulating flipping a coin with this box model. And so that's step one. Why did we have to do step one? Well, because in step two, it says to find the expected value and standard error of the sum. So the expected value of the sum is n times the average of the box. All right, and that's why it's nice to draw your box, because then you can easily find the average. I know the average up here is just 1 plus 0 divided by 2, right? 0.5. And then I'm going to need the SD too. Do you guys know what the SD is? SD of this box? Anyone? 0.5. I hear some people saying it. Yeah, it should be 0.5, half ones, half zeros. So I could do the shortcut formula if I wanted to, or I could just say there's half ones, half zeros. I know the SD is 0.5. On the homework last night, you guys should have saw that for 0, 1 boxes, this is the biggest the SD can be, 0.5, all right? And then, so for 0, 1 boxes, the SD ranges between 0, because it can't be negative, and 0.5. And 0.5 is when it's the biggest. That's when you have half ones, half zeros. Question? So for how big, that's what's the biggest sum, I think is what you're talking about. Like, what's the biggest sum I could get out of here? Yeah, that would be 100, right? You could get 1 every single time. For the SD, technically, if it's not a 0, 1 box, the SD can be as big as you want it to be. But for 0, 1 boxes, the biggest it can be is 0.5, just because you're always taking the absolute value of 1 minus 0 and then multiplying that by some fraction. So 0.5 is the biggest the SD can be, specifically for a 0, 1 box. Any other questions? Yeah. How do you find the SD if it's not just 2 tickets? You guys won't have to do that, but basically you'd have to do what we did in chapter 4, like do the 5 steps, take the average, find the deviations, chapter 4 stuff. But like I said, you guys won't have to do that on this test, on exam 3. The midterm exams are not cumulative. So, okay, now that we have this, now I can find this. So expected value of the sum is just n, which is 100, times the average, which is 0.5. This one also, I didn't really have to do the formula. I could have just said, if I toss a coin 100 times, how many heads am I expected to get? And it should be 50. All right? And then next, I need to find the standard error for the sum. All right, so that's the square root of n times the SD of the box. So square root of 100 is 10 times 0.5 gives me 5. Okay, so the question still remains, why are we doing all this? Well, the original question was this: in 100 coin tosses, what's the chance of getting less than 45 heads? So what I need to do is mark 45 on this normal curve. But remember, our normal curve is measured in z-scores, so I'm still going to label my x-axis like I always do. So basically what I'm going to do next is convert our value to a z-score. This is just like we did before. So 45 I need to convert to a z-score, and our z-score formula before was value minus average divided by SD. That was when we were dealing with just regular variables. Now that we're dealing with the random variables, it changes slightly. Instead of average and SD, we have expected value and standard error. But it's the same exact thing, just for random variables. So this is what I'm going to use, right? Because the expected value is what I'm expected to get, and then the standard error is the give or take. Expected value is like the average, standard error is like the SD. So looking at that, so I want to figure out how many standard errors is 45 away from the expected value. So let's go ahead and do this. I have value minus expected value divided by standard error. That's the general z-score formula. And I'm going to add, for this one, I'm dealing with sums, so I'm just going to add that we're specifically talking about the sum. And if I do this, my value is 45. That's what I want to mark on the curve. And then I found in step 2, my expected value was 50, and my standard error was 5. So basically, this is just -1. So if I mark, so now I'm going to use the normal curve. And this is where once you get to a z-score, it's just the exact same thing that we've done before. Here is, this represents 45 heads. So if I made another kind of x-axis down here to represent the amount of heads, 50 would be in the middle. The expected value is like the average, so that's right in the middle. So these are the amount of heads. And then these are the z-scores. Okay, and then I'm going to shade. I want to know what's the chance of getting less than 45 heads. So I'm going to shade everything to the left. All right, that looks good. And then to find this probability, I would just look up my z-score. It's -1, so if I look up 1, this is one we see all the time. This is 68%, right in the middle. And then I think everyone remembers how to get these tails. We just take 100 minus 68 divided by 2. So the chance, my final answer, is 16%. What's the chance of flipping a coin 100 times and getting less than 45 heads? That's going to only be 16%. Okay? So this -1, this is my z-score. This means that if you get 45 heads, so this is the z-score for 45 heads, so this means 45 heads is 1 standard error below the expected value. All right, so the expected value is 50, and then if I go 1 standard error below, I get right at 45. Okay, so like I said, pretty much the same thing as before, except now we're changing up and dealing with random variables. So I have expected value and standard error instead of average and SD, but it's interpreted basically the same way, just replacing those two statistics. All right, any questions on this? Okay, we'll do this next example. This is kind of the same thing. It says, in 100 coin tosses, now they give us a range though. What's the chance of getting between 40% and 60% heads? All right. So you can do these types of problems with anything. Like, for example, if you you could figure out, if I guess on the final, if we have a final that's 100 multiple choice questions and you completely guess on every single question, what's the probability you'd get above a 50%? You can do that using the normal curve, just like this. So these are coin examples, but we'll do some other examples too. Okay, so we already did this. Step 1, right? Draw the box model. It's the same as on the other page. 1, 0, and then we have 2 tickets. The coin's the easiest one probably, and the average is 0.5, and the SD is 0.5. So it's the same box model. Draw your box for a single draw, and then step 2, it says to find the expected value and standard error for the percent. Because now we're dealing with, I know I'm dealing with percents because I see the percent signs. And I'm going to use these to help me convert 40 and 60 into a z-score. So the expected value of the percent is just the percent of, and then in this case, what am I dealing with? Heads. So the percent of heads in the box, which is just 50%. So this one also, you can just think, if you toss a coin 100 times, what is the percent of heads you're expected to get? Should be 50. Give or take what? Well, the standard error for the percent is just, it's the same thing as the average, but multiply it by 100. So it's the SD of the box divided by the square root of n times 100. And I have all of this stuff. I have the SD is 0.5, N is 100. And then when I multiply by 100, I'm getting everything in percent form. So for all these, you'll notice I keep it as 50%, not as 0.5. That's because then I can use these formulas. So this ends up being 5%. So pretty much the same as I got on the other page. All right, and then now I can answer my question. I have everything I need to know. It says convert the two values to z-scores and find the area in between. So for z-scores, I'm just going to use the formula, which is value minus expected value divided by standard error. And that's for these random variables. And I'm dealing with percents, so I'll just add the percent signs. Okay, and I have two of them, so I want to know what's the chance of getting between 40 and 60% heads. I'm going to need to convert both of those into z-scores. So my normal curve, my z-scores are going to be somewhere in here. We can do 40 first. The z-score for 40% is just going to be, so 40 is my value, 40, 50 is my expected value, and then I get 5 for my standard error. So those are from step 2. And let's see, negative 10 over 5 is negative 2. So that means getting 40% heads is 2 standard errors below what I would expect. So this is 40% heads. And then right in the middle, that's my expected value. That's the 50%. So I can tell right away, 60, when I find the z-score for 60%, that is going to be above, is going to be positive, right? Because it's above 0. It's above the expected value. And as we can see, the z-score for 60 is just going to be positive. 60 minus 50, so 10 over 5 is positive 2. So this one, pretty straightforward because the z-scores are exactly the same. One of them is positive, one of them is negative. All right, so standard units or z-scores, these are the percent heads. And then I want to shade everything in between. I want to know what's the chance of getting between 40 and 60% heads. All right, that looks good. And then to find this out, this one, now I don't have to do anything crazy. I'd basically just look up the z-score for 2, and that gives me the middle area. The area between 2 and negative 2 is 95%. And that makes sense. Think about when you're doing these types of problems, what's the chance of getting between 40 and 60% heads? That's what you should get. So that's actually 95%. Okay, any questions on this? All right, that looks good. So we have this next, okay, page 155. So what does this say? This is an example from chapter 15 revisited. 36 straws, that's my N, that's my sample size, number of draws, are made at random with replacement from this box. This box, I can't find the SD for it, right? I can't use the shortcut formula, so I'll just tell you guys that the SD is 3. And then I'm just going to have you guys do part A. You'd expect the sum to be what? Give or take what? So this is going to be our first side clicker question. Part A, 36 straws, and you know the SD is 3. So let's get back to this. Here we go. I'll give you guys a minute. I'm going to ask about both. What would you expect, and then the give or take part. So go ahead and do both of those. All right, does anyone need more time? You guys good? Okay, you'd expect the sum to be, let's see, you guys got it. Should be 108. Expected value of the sum. N times the average of the box. That looks good, give or take. And then what's the standard error? All right, let's see this one. I didn't stop it yet, but it looks like D is winning. It should be 18. Square root of N, so that's square root of 36, which is 6, times the SD, which is 3. That is exactly right. I think everyone's good with these formulas. You'll get plenty of practice with them throughout the rest of the semester, but there is my work. 108 and 18, which is exactly what most of you got. Now, the second part, this is the new part of it. What's the chance that the sum of the 36 straws would be greater than 120? So again, we need to mark 120 on this curve and shade the area to the right. Okay? So to do this, I need to convert 120 to a z-score. And remember, the z-score formula is the same as before, except now it's value minus expected value divided by standard error. So I'm using basically the average and the SD for random variables. And I'm dealing with sums, so I can add that. The value that I'm concerned about is 120. So I need to figure out 120. I know it's above my expected value. My expected value is right in the middle, 108. So 120 should be somewhere over here. I should have some sort of positive z-score. So minus 108 divided by 18. And I end up getting 0.7. So if you get, basically if you draw out of this box 36 times and you get a sum of 120, you're 0.7 standard deviations above the average. But we're dealing with random variables, right? So I'm 0.7, technically I'm 0.7 standard errors above the expected value. And then I'm gonna shade this, everything to the right. All right, and now what do I do? Let's see, so I'd have to look up 0.7. The only thing I can really do to figure out that blue shaded area is look up 0.7. So on exam 3, just like the first 2 exams, you guys will get the normal table. So I'd go down to 0.7, there it is. Middle area is about 52%. Okay, 52%. And then again, just to get this, I'm going to take 100 minus 52 divided by 2 to get the tail. And that gives me 24%. So that is the answer. What's the chance that my sum will be above 120? About 24%. Okay. So now, part C says you'd expect the average of the 36 straws to be what? So let's do this one really quick. If I change it to average, how does that affect what I'm expected to get? So you'd expect the average of the 36 straws to be what? Okay, average. Let's see what you guys got for this. What would you expect the average to be? Give or take what? So let's see. A, nice. Should be 3, right? What would you expect the average to be? The average of the box. That's exactly right. That is the formula. Expected value of the average is just the average. And now what about the standard error? What is the give or take part? Okay, it looks like most people are getting this one too. It should be B, it should be 0.5. That looks great, 87% and going up. All right, so answer that if you haven't already. I showed my work on the notebook right here, just using the formulas. And then again, just doing this is the same thing. What's the chance that the average of the draws would be less than 4? So I'm expected to get 3. So 3 would be right in the middle. 3 would be right here. So 4 is going to be a positive z-score as well. Let's go ahead and figure that out. It's just going to be the value minus the expected value divided by the standard error. And then the value is 4. What's the chance the average will be less than 4? So I have 4 minus 3 divided by 0.5. So expected value and standard error. And that gives me, let's see, 1 divided by 0.5 is 2. So if you get an average of 4, if you draw 36 times and your average is 4, you are 2 standard errors above the expected value. And so the question asks, what's the chance that the average will be less than 4? So I want to make sure to shade all of this area to the left. Okay, and then to find that, I know 2, the z-score is 95, so the middle area is 95%, but that's not going to be my answer because I want the middle area plus this left-hand tail. And to get the tail for 95, that is also just 100 minus 95 divided by 2, so that's 2.5%. So 95, then my final answer, what's the chance the average is less than 4? 95 plus 2.5. So that is 97.5%. Okay, any questions on that? All right, that looks good. Let's go to the next page. This bottom one is literally just the same thing, except we're dealing with percents. We want to know what's the chance the percent would be more than 60. Convert 60 to a z-score, shade the area to the right. So same kind of thing. We'll come back to this next week if we have time, but I want to make sure to do this question up here on the next page. It says you play roulette 100 times. All right, 100 times, that is my N. All right, so N for so far, again, just to reiterate, N is the number of draws, and it's also, you can think of it as the number of times you play the game. I know some people were getting confused with the number of tickets. N is not the number of tickets. N is the number of draws. So the number of tickets is just the amount of outcomes you have if you play the game once. All right, so we play 100 times betting $1 on red. What's the chance you'll win more than $1? All right, that's my question. And it says, remember the roulette wheel. There are 38 slots, 18 red, 18 black, 2 green. All right, so what's the chance you win more than $1? So this is kind of an applied question. And basically what I would want to do is mark $1 on this normal curve. Okay, mark $1 and shade everything to the right, because I want to know what's the chance you win more than $1. But I don't want to put that at 1. I don't know if $1 corresponds exactly to a z-score of 1. I have to figure out what it is. What is $1 in terms of a z-score? So with these questions, it's always easiest to draw your box first, then find your expected value in standard error. Then lastly, the very last thing we want to do is change $1 into a z-score and find the area. All right, so I'm going to draw, so for roulette, we've done this before, right? We want to draw our box for one spin. For one spin of the wheel, and we've seen this box. We know that on one spin, the ball can land in 38 different slots. So I'm going to have 38 tickets. And we've specifically, I think, done this one where we bet $1 on red. So on the tickets, you can either win $1 or lose $1. And then we want to say how many ways are there to win, how many ways are there to lose. And if we're betting on red, there's 18 reds, and then there's 20 other colors. So there is my box model, the classic roulette box model if you're betting on red. And now that I have that, I should be able to find my expected value and standard error. And the question is, which one am I going to use? I don't see... Looking through this problem, I don't see the word sum, I don't see the word average, I don't see the word percent. So what do you guys think we should use? Sum, good, because we're basically, if it doesn't say average or percent, we're going to use sum. We're adding up how much we win and lose. And we've done this before, right? We've done this exact question, I feel, this problem. Not this part, but this part. So you're right, we're going to use sum. So expected value of the sum is n times the average of the box, 100 times, and then the average of this box, to find the average of the box, I would just take all these tickets and divide by 38. So I need to add up. There's 18 ones plus 20 negative ones. And I get my standard average for roulette, which is -2 over 38. Okay, so 100 times and then -2 over 38. And we'll see what that gives us. I'll put that in my calculator really quick. -5.26. I think we've seen this one before, but yeah, -5.26. So there's my expected value. And now I need my standard error. I need that. So the standard error is going to be the square root of n times the SD of the box. And here, I don't have the SD, but I can find it, right? Because there's only 2 types of tickets. I just have ones and negative ones. So I can find this using the shortcut formula. So when I do that, the SD shortcut formula, it's just the absolute value of A minus B. So A and B are 1 minus -1. All right, so don't forget, I know we've been doing a lot of 1, 0 boxes, but don't forget, if they're not 1s and 0s, we have to do this part in front. And then times the square root of, it's the fraction of A tickets, so the fraction of 1s is 18 over 38, times the fraction of -1s is 20 over 38. And let's see what I get. So this is 1 minus -1 is 2, right? So I have 2 times the square root of 18 over 38 times 20 over 38. And I get, can you guys see that? 0.9986. I'm just going to round that to 1, 0.9986. So this is about 1. Standard deviation is basically 1. So square root of 100 times 1 is 10. Okay, so I did step 1. I did step 2. Now let's do step 3. Step 3 is to convert our value to a z-score. So I'm going to use the same thing we used on the other pages, value minus expected value divided by standard error. And I am, like you guys told me, dealing with sums. And that is a good rule to go by. If it doesn't say average or percent, assume it's sum. And my value is $1, okay? Because I want to know, I'm expected to lose $5.26. Well, I want to know what's the probability I win more than $1. So value minus, my expected value is negative, which is okay. That actually does make sense, divided by standard error. And then my z-score ends up being 0.6. So right in the middle, so this is in z-scores. If I wrote the dollars below it on my normal curve, right in the middle, my expected value is negative 5.26. And then $1 would be right here at 0.6. 0.6, that would be $1. And then I want to shade the area to the right. What's the chance I win more than $1? This is a legitimate question if you're playing roulette, because that's probably what most people care about. Do they win? Do they win, basically? What's the chance I win more than $1? You could also figure out, like, what's the chance? Maybe you don't want to win $1. Maybe you'd rather win more. Figure out what's the chance you win $20. 2, we just do the same thing, except use 20 instead of 1. So now, to find this, I'm going to do, let's see, I'm going to have to look up 0.6, right, to get my middle area. That ends up being 45% in the middle. So then the chance that I win more than $1 is, let's see, what is this? 100 minus 45 divided by 2. And I get 20. Not dollars, 27.5%. Okay, any questions on this? All right, we're gonna do one more because I wanna ask you guys a question. It says suppose you play roulette 900 times, all right? So N goes up. What's the chance you win more than $1? So now I want to know, okay, the more I play, should my chance go up or down? What's the chance you win more than $1 in 900 plays? The chance, this right here is the chance, this is the chance I win more than $1 in 100 plays. All right, 27.5. So my question for you guys, if I do the same, basically this is the same as example 9, except N is bigger. All right, N is bigger. 900 instead of 100. So if I play 900 times, this is just before we actually do this and figure it out, I want to ask you guys, what do you think? Do you think the probability is going to be bigger than 27.5? Is it going to stay the same? Is it going to be smaller? What is your intuition? So do you think the probability of winning more than $1 will increase, decrease, or stay the same? This one, I mean, there is a right answer, but I just want you guys to take a guess. Before we do the math, what would you say if someone asked you this question? Okay, let's check. Vote if you haven't already. Interesting. Okay. Most people, 50% of the class exactly says increase. And then we got 33% saying decrease, 17% saying stay the same. Well, let's check. This shouldn't be too bad because I have the same box, right? It's roulette. I have the same box, so I have the same average and the same SD. The expected value is going to change though, right? Because the expected value of the sum, if I look back up here, it was n times the average of the box. Now n is 900, right? N is 900, so my new expected value is going to be 900 times, but the average is the same, negative 2 over 38. And then my new standard error, my standard error is also going to change. I have the square root of n. So instead of the square root of 100, I have the square root of 900 times the standard deviation is still 1. All right, and these end up being, let's see, this one is negative 47.4, and this one is 30. So sure, you're expected to lose more the more you play, but also there's a bigger standard deviation, or bigger standard error, both, right? There's a bigger standard error, for sure. So now let's mark down, what is our question? What's the chance I win more than $1? Well, I have to do the same thing I did up here. I have to convert $1 to a z-score. So that's just my value is $1. And now I'm going to do the same thing except use my new expected value in standard error. So I'm going to use negative 47.4 and 30. All right, and then my new z-score, so my z-score does change a bit. It ends up being 1.6. All right, so 1.6. So here's my expected value, negative 47.40, and $1 is up here at 1.6. There's $1. And I want to know what's the probability I win more than $1. And right away I can see my shaded area is smaller, right? It's smaller than this. So if I figure out exactly what this is, I'd look up 1.6. My middle area is 89%. And then the chance that I win more than $1, this shaded area, is going to be 100 minus 89 divided by 2. And that gives me, what, 11 over 2. So this is 5.5%. So I guess the people that said decrease are correct. Basically, if you have a negative expected value, the more you play, the less probable it is that you'll win a lot of money. All right? So that's all we're going to do for today. This next page, we're skipping the next page, just FYI. So I'm going to not start here. I'm going to start on the next one.